Now, I'm looking for RB. So in order to find RB, first I find IB. And I can find IB because I know IC and I know HFE. So I'm going to use the HFE equation. HFE, what's the formula for HFE, everybody? IC over IB. So if I manipulate this and write it for IB, how can I write it? Would it be IC over HFE? Okay, so that's what I'm going to do. I know the value of IC, which is 5 milliamps. My Q point. HFE, 150. It's given, isn't it? So that's how I calculate IB. What's 5 milliamps over 150? 33 microamps. By the way, be careful in how you write your micro. Always show the line longer on the front side of the U, because some people do this, and it's hard to distinguish between an M and an A if you don't write it properly. Okay, so this is bad practice. This is the right way of showing the micro. Okay, so that's 33 microamps. Now that I know that IB is 33 microamps, I can find RB. Again, using Ohm's law. RB is equal to V over I. I know that I is 33 microamps. What about V? Voltage at RB is the voltage at the top minus the voltage at the bottom. Voltage is always across 2 points. Voltage at the top, voltage at the bottom. How much is the voltage at the top?
4.5.
VCC, 9 volts. What about the voltage at the bottom, right here? That voltage is the voltage across the base to emitter. So VBE divided by IB. Everybody see that? This is 9 volts, which is the voltage on one side of the resistor. VBE is the voltage on the other side of the resistor. So that is 9 minus, and the voltage from the base to the emitter is the voltage across this PN junction here. NPN. This PN junction in a silicon transistor is 0.7. Close to 0.7. Divided by 33 microamps. What do you get? 100? 151 kilo ohms? 251. 251 kilo ohms. Okay? So, this is what you're going to be doing for the pre-lab for this week, is to design a circuit like this, and then you'll get a value like 251 or something like that. And if you don't have that value of resistor in your kit, then what you do is you take a couple of resistors, connect them in series, so it becomes close to 251. And if you don't have 900 ohms, then you do the same thing here. You hook up a couple of resistors so that you're close to 900. Doesn't have to be exact, but close to that value. Okay, so that's what we're going to be doing in the lab this week.
How close is close? Like, for the 900, like 100 ohms would be close?
100 off?
Yeah, or like less than that.
If you get 800 ohms, that would be way off. Okay, but if it is 880, then that would be okay. Yeah, so you don't want to be way off.
What if you use the pot instead?
Yes, pot is good. If you use a potentiometer there, set it to 900 ohms, that is perfect. So that's page 8. Page 9. This, yes. Meaning? Yes, 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 yes. By all means. Okay. When I say label everything, that means that you want to show the axis, VCT, IC, 0, and Q. Page 9. Disadvantage of base bias circuit. What we're saying there is that with this base bias circuit, anytime that you have some temperature change, this circuit is very sensitive to temperature. So a little bit of an increase in temperature and your Q point will start shifting a little bit. Okay? So IC will change, VCE will change, and that's not good when it comes to the amplification of a circuit. And that's why this kind of a circuit, it says in number 4, is mostly used for switching type of a circuit. And a switching type of a circuit is where you are not concerned too much about the points in between, close to the middle, but you are more worried about staying close to the cutoff or close to the saturation. So base bias circuits is used almost exclusively in switching circuits and not in amplifier circuits that much.